laws of large numbers. In the last lectures, we covered different modes of convergence. Two of the applications of the convergence concepts are the laws of large numbers and the central limit theorem. So, two important results, in fact celebrated results, that is, number one is laws of large numbers, and number two is central limit theorem. So, laws of large numbers and central limit theorem are concerned with the behavior of the average of large number of random numbers. Suppose we have a large number of random variables, we average them, and how that average will eventually behave, that answer is given by laws of large numbers and central limit theorem. Now, these results, that is theoretically very important, laws of large number and central limit theorem, theoretically they are very beautiful results and they have several areas of applications, which we will be covering in this class and subsequent class. First we will discuss laws of large number. Basically, this laws of large number is concerned with the behavior of sample mean. What is sample mean? Consider a sequence of random variables and suppose each has mean, average value or expected value mu I. Then we define the partial sum Sn is equal to summation xi going from 1 to n. This is the partial sum, and if I divide it by n, then I will get the average. So, now this partial sum Sn divided by n is the average. Now, how this average behaves, that is the question. First of all, let us consider the expected value of Sn by n, because Sn by n, how do I define? Sn by n is equal to summation xi I is equal to 1 to n divided by 1 by n. Now, this quantity is a random quantity because these values are random. So, naturally we can find out what is the average value of this random quantity E of Sn by n. So, that quantity, because it is a sum of random variables, so expected value will be also sum, therefore, this will be 1 by summation E of xi I is equal to 1 to n divided by n, and as we know that E of xi is mu I. So, therefore, I can write this is equal to summation mu I is equal to 1 to n divided by n. So, what we have seen that E of Sn by n is equal to the average of the true means. Average of the true means. Each of the random variable has a mean mu I, therefore, we are taking the average. So, this quantity Sn by n has an average value which is the average value of the true means. So, on the average, that means on the average Sn by n is equal to the average value of the true means, but whether Sn by n actually approach this quantity. So, for that we have to see the variance of this quantity Sn by n, what is the variance. So, let us see that. So, if that variance becomes smaller and smaller, then we can say that Sn by n approaches this quantity as n tends to infinity. So, that way we get this statement of the laws of large numbers. Let us first give these statements. the sequence of random numbers or random variables xn is said to obey the weak law of large numbers, that is we write it as W L L n, W L L n. If Sn by n that quantity converges in probability to the average of the true mean. So, what is the weak law of large number? That Sn by n, this is a quantity we are concerned with, that is the sample average. If it converges in probability to the average value of true mean, then we say that this sequence of random variables xi's, they obey the weak law of large numbers. So, weak law of large numbers, because here convergence is in the weak sense, that is why this is known as the weak law of large number. Now, the sequence xi's, if it obeys the weak law of large number, that it means that this Sn by n converges to the average of the true mean in the probability sense. So, this is the weak law of large number. Similarly, the sequence xn is said to obey the strong law of large numbers if this average, sample average or sample mean converges almost sure to the average of the true mean. So, this is the strong law of large number. What does it say? That Sn by n, that is the sample mean. Now, as n tends to infinity, this is convergent and it converges almost sure to the average of the true mean, summation mu I is equal to 1 to n divided by n, average of the true mean. Then we say that this sequence xn obeys the strong law of large number. It is abbreviated as SLLN. So, we have to see under what condition weak law of large number is true and under what condition strong law of large number is true. But both are concerned with the behavior of the sample mean as n tends to infinity. We will state one theorem. Theorem 1, weak law of large numbers. Suppose xn is a sequence of random variables defined on the probability space SFP with finite mean mu I for each of xi. If we impose this condition, limit n tends to infinity of the double sum of covariance of xi xj divided by n square. If this limit happens to be 0, then Sn by n converges in probability to the average of the true mean. So, we impose the condition. What is the condition? If summation, that is double summation, covariance of xi xj, summation over I over j, but j not equal to I, because covariance between two distinct random variables, divided by n square. If this limit n tends to infinity is equal to 0, then we can say that this sequence xn obeys the weak law of large numbers. So, that means that sample mean converges in probability to the average of the true mean. Now, this covariance of xi xj means E of xi, this quantity is nothing but E of xi minus mu I into xj minus mu j. So, this quantity is the covariance. We have to prove that Sn by n converges in probability to the average of the true mean. But convergence in probability directly proving is difficult. So, we will first see if it is convergent in mean square sense. That means, we will see this quantity E of Sn by n minus summation mu I I going from 1 to n divided by n. This is the quantity which left hand side should converge. So, we consider the convergence in the mean square sense. So, that way we consider the mean square value here, and this if I write the values of Sn as the summation of xi, then I can write this as because 1 by n is here, if I since it is square value is there, this 1 by n square can come out into E of now sum of the deviation. So, we are considering xi minus mu I. So, this sum going from I is equal to 1 to n. So, this deviation sum square. So, we want to find out this quantity. Okay. Now, this we see that this is a square of the sum. So, we can break it in terms of the individual square and then the cross terms. So, individual square terms are there, cross terms are there, and then we can take the expected value. So, that way we will have this quantity first, E of xi minus mu I whole square, this sum plus the covariance sum, and each sum is scaled by 1 by n square. And we notice that E of xi minus mu I whole square, that is the variance sigma I square. So, I can write this as variance sigma I square summation I going from 1 to n. Similarly, this term is covariance of xi, covariance of xi minus mu I. So, this quantity is the covariance of xi xj. So, that way we have this quantity, this mean square value is equal to summation of variance divided by n square and double summation of the covariances divided by n square. Now, our aim is what happens as n tends to infinity. We are given that this quantity is finite, sigma I square, that is a finite variances. So, each of the random variable has finite variance, and also we are given about this summation. So, let us see. So, if I have to take the limit of the left hand quantity, this mean square value as n tends to infinity, therefore, I will have the limit of this quantity and limit of this quantity. Now, limit of this quantity is equal to 0 because this sigma I squares are finite, and this limit is also 0 because already given that this is according to the condition given in the theorem, this quantity is equal to 0. Therefore, what we will have that this quantity, that mean square value as n tends to infinity, limit of this mean square value is equal to 0. So, what does it imply? This implies that Sn by n converges in the mean square sense to summation mu I is equal to 1 to n divided by n, average value of the true means. So, we get this result. So, this also implies that now we know that mean square convergence, MS convergence implies convergence in probability. So, what we conclude that Sn by n, that is the sample mean, converges in probability to the average of the true mean. This is the weak law of large numbers. So, we have established one theorem. According to this theorem, what we require? We require, suppose if we are given a sequence of random variables xi's and each has some finite mean mu I and finite second order moment, that way variance is also finite, and if we have this condition summation of double summation of covariance of xi xj, this is over I not equal to j. So, if this double summation of covariance of xi xj scale by 1 by n square is, if this is equal to 0, limit of this is equal to 0, if this is limit of this quantity is equal to 0, then Sn by n converges in probability to the average of the true mean. So, this is the weak law of large numbers. So, this is the condition we need to be satisfied. Okay. Now, what we gave is a general statement. Now, we can derive several simple cases. Suppose these special cases of weak law of large numbers are, suppose A is xn is a sequence of independent and identically distributed random variables. So, if xn is known to be independent and identically distributed, because suppose same random variable we are observing suppose at different instant of time. For example, if I am tossing a coin and corresponding outcome is a random variable, suppose Bernoulli random variable which takes value 1 and 0. Now, this is a sequence. If I go on independently tossing the coin, then I will get a sequence, that is a sequence of i.i.d. Bernoulli random variables. So, that way if I have an i.i.d. Sequence of random variable, in that case this condition will be automatically satisfied. The condition for weak law of large numbers will be satisfied because it is a i.i.d. So, mean is in this case will be constant, and because it is independent, covariance of xi xj will be automatically 0. Therefore, Sn by n in probability it will converge to mu, because now summation that is average of mu I is equal to nothing but its mu I is mu. So, n mu divided by n, that is equal to mu. So, therefore, Sn by n in this case converges in probability to mu. So, this is one special case. Similarly, now we can drop the condition for identically distributed. Only what we require is, suppose mu I is given E of xi and the sequence is independent. Xn is a sequence of independent random variables. So, in that case independence implies uncorrelatedness. Independent implies uncorrelatedness. What does it say? That is uncorrelatedness means covariance of xi. Suppose if xi and xj are the random variables, then covariance of xij will be equal to identically 0. So, in this case also because this will become 0 because of independence condition, therefore, Sn by n will converge in probability to the average of the true mean. So, this is case 2. Similarly, we can consider further relax, because what we require is that covariance of xi xj is equal to 0. For that, this sequence need not be independent. If the sequence xn is a sequence of uncorrelated random variables, then also we will have covariance of xi xj, automatically it will be equal to 0 because of the definition of uncorrelatedness, and therefore, Sn by n converges in probability to mu. So, these are special cases, but generally what we require that this quantity, that is this covariance sequence So, this covariance sequence has the property that if I consider the sum and then divided by n square, then this quantity, limit of this quantity is equal to 0. So, if we have suppose other conditions also, we consider 3 special cases A, B and C. Other than that, anywhere where this sum becomes 0, summation, that is summation xi minus mu I into xj minus mu j, expected value of that is the covariance. Summation, this is a double summation over I and j not equal to I divided by n square. If somehow this sequence goes down to 0. So, ultimately depending on the property of the covariance sequence, this weak law of large numbers are obeyed. If this condition is satisfied, then covariance satisfies this condition, and of course other condition is if a mean is, of course mean need to be finite and variance also needs to be finite. In that case, Sn by n will converge in probability to the average of the true mean. That is the weak law of large number. That is sample mean converges to true mean. As n tends to infinity. So, this is a very powerful result. That means, what we expect that this quantity under the condition already stated, this Sn by n will be as close as possible to the true mean. If we are considering only i.i.d. case, for example, with constant mean, then this Sn by n can be made arbitrarily close to true mean. Sn by n converges to mu in probabilistic sense. For example, if I consider suppose measurement of a constant quantity, maybe that constant quantity itself is mu by means of some noisy observations. Now, these observations are suppose x1, x2 up to xn etc. These are the observation, noisy observation of the same constant quantity mu. Now, that means x1, x2, xn etc. they are the random variables because of the noise. Now, they represent a constant quantity, that is expected value of this E of xi's r, E of xi's will be equal to mu. Is E of xi is equal to mu. Then what this weak law of large number says that if I take the sample mean, so summation xi I is equal to 1 to n divided by n. This is the sample mean. What is this? This is the average of the noisy samples. Average of the noisy samples that will converge to true value, to true mean. Now, this quantity is the unknown quantity which we want to observe or which we want to measure. So, because measurements are noisy, we take the sample average, and this sample average, as we are taking more and more number of observations, then this sample average will be close to mu. So, that is our belief. We generally in our any experiment we do that way. If we have number of observations, then we take the average, so that average is more close to the unknown quantity. So, that is a consequence of weak law of large numbers. There are several other consequences. For example, the interpretation of probability as relative frequency, that can be easily explained in terms of weak law of large numbers. We will now consider the strong law of large number. So, this is the consequence of almost sure convergence. So, strong law of large number is concerned with convergence almost sure or convergence with probability 1. So, what this theorem says? First of all, when this sequence, we have a sequence of random numbers. So, that sequence obeys strong law of large number if sample average converges to the average of the true mean almost sure. That is the strong law of large number. If sample average converges almost sure to the average of the true mean. So, that is the strong law of large number, but we will be considering a special case of strong law of large number, that is Kolmogorov's strong law of large numbers. It says that if xn is a sequence of i.i.d. random variables, here we are concerned with only i.i.d. independent and identically distributed. With common mean mu, we are considering the special case, common mean mu and finite variance. So, if we impose this i.i.d. condition, then Sn by n converges almost sure to mu. So, it converges almost sure to mu. So, we will try to prove a special case of this. So, this is the strong law of large numbers. Suppose we impose this condition, this sequence, this is i.i.d. with constant mean mu and finite variance, but we also require that finite fourth order moments. So, this is the fourth order central moment E of x n minus mu whole to the power 4, that is less than infinity, that is finite. We require that we impose the condition that this sequence, it is a sequence of i.i.d. random variable, but it is a restricted case where the fourth order central moments are also finite. So, in that case we will prove that Sn by n converges in almost sure sense to mu. So, what we want to prove then? We want to prove that that is Sn, suppose Sn by n minus mu, this deviation, suppose if I consider the deviation of this is greater than m. Suppose we consider the all sample points for which this happens. So, what we require is such that this deviation from mu is greater than 1 by m. If we consider this event, okay. Now, we will consider the limb soup of this event as n tends to infinity. So, we can define the limb soup of this deviation. So, we are considering all those s for which there is some deviation, and here m is greater than, it is a positive integer greater than 0. So, now what we require is that probability of this event should be equal to 0. So, convergence almost sure means this quantity, that probability of limb soup as n tends to infinity of those values of s for which Sn by n minus mu, that deviation is greater than 1 by m. So, if I consider the infinitely often happening those deviations and probability of all those deviations, infinitely occurring deviations, the probability should be equal to 0. That is the condition for almost sure convergence. So, we will prove this first. This again, this also will be proving using the Markov inequality. Markov inequality and Borel-Cantelli lemma, BC lemma. So, because we are given a condition on fourth order moment, so we will be examining the fourth order moment first, that is E of Sn by n minus mu to the power 4. So, this is, if I simplify this, then I will get an expression like this, and this quantity now I will denote by yi, so that yi is a 0 mean random variable now. So, yi is equal to xi minus mu. So, that way yi is a 0 mean, it is 0 mean, E of yi is equal to 0. So, but here this quantity is summation of yi to the power 4. So, it will, because it is a power 4, we can expand it, and in the expansion we will have terms like this yi to the power 4, then yi cube yj, then square terms, then yi yj yk square, etc. And we have to take the expected value of each of the terms. But if we observe closely, then we see that what will be the expected value of any term involving yi cube, because these are independent sequence we are considering, i.i.d. sequence. Therefore, expected value, for example, if I consider the expected value of E of yi cube yj. So, what it will be? That will be equal to E of yi cube into E of yj. Now, E of yi cube, because yi is a 0 mean, it is a centered around mu. So, that way this quantity will become 0, this quantity will also become 0. So, because of that this will become 0. Similarly, all odd moments will become, wherever any odd term is there, suppose this term yi yj. So, this is yi is there, yj is there, yk square is there. Because of yi and yj, this term will also, expected value will become 0. Similarly, if I consider the expected value of this will become also, this will also become 0. So, with this observation, now if I have to expand this expansion can be simplified. I will have only this quantity. So, this will be 1 by n to the power 4 into n e yi to the power 4 plus n c2 into 4 c2 into e of y I square whole square. So, this we can further simplify, and we can write like this. Okay. We are just writing the expansion for NC2 and 4C2, and therefore, we will get like this. Now, we are considering as when n is large. Now, suppose if I consider this quantity, if I take n outside, then this will be n square. So, that way I can write this equality in terms of this inequality, because this is a some constant k divided by n cube plus 1 by n square into k2. All other terms, suppose we consider this quantity and 3 etc. all combine into this k2. So, what we get is that yi, I know that is xi minus mu. So, that is fourth power of the average, expected value of that will be less than equal to k by n cube plus 1 by n square into k2. So, this is the result we have established. Now, let us see. So, we are interested to determine the probability of the deviation. So, probability of S such that Sn by S, Sn by n minus mu, that deviation is greater than 1 by m. So, this is the event. We are considering the probability of the limb soup as n tends to infinity of this event. So, this is a sequence of event is there because Sn by n is there. So, we are considering the limb soup of this, and probability of this limb soup should be equal to 0, that we want to establish. So, for that we consider this event. So, probability of this event. Now, essentially we want to apply the Borel-Cantelli lemma. For this we want to evaluate this probability. Now, this probability is same as probability if I both side, if I take the fourth power and right hand side also fourth power. So, that way this probability is same as this probability. This is less than equal to, now we can consider the expected value because we can apply the Markov inequality. Now, Markov inequality we apply, Markov inequality. So, because of Markov inequality we will get that this probability is less than equal to this quantity. Okay. So, now we have already established that this is less than equal to M4, because M4 will come because of this into k by n cube plus M4 by n square into k square, okay, into k2, M4 by n square into k2. So, now if I have to consider the sum of this probability as n tends to, for n is equal to 1 to infinity, that is infinite sum of this probability sequence if I consider, wherever there is a deviation, all probability if I sum up. Now, that will be less than equal to sum of this quantity, and I know that 1 by n cube is a convergent series, 1 by n square is also a convergent series. So, this sum will be finite. So, we got a condition that the sum of these deviation probabilities is less than infinity. Now, we can apply the Borel-Cantelli lemma and so prove the theorem. So, now it is simple because this condition is satisfied. So, this part is my Sn by n. So, what does it say then? This implies that Sn by n, this is a condition for almost sure convergence, Sn by n converges almost sure to mu. So, this is the consequence of Borel-Cantelli lemma. So, this is this strong law of large number. Therefore, what we have established that probability of limb soup of the event as such that Sn by n, that is the quantity of our interest minus mu, that is greater than equal to 1 by m. This is 1 by m. So, limb soup of that is equal to 0. This implies that Sn by n converges in almost sure sense to mu. So, this is the strong law of large number we have established for a particular case where the fourth order central moments are finite. For the sequence considered, fourth order central moments are finite, and in that case if xi's are i.i.ds, then the sample mean converges almost sure with probability 1 to the true mean mu. This is the strong law of large number. So, that way we discussed about weak law of large number, which requires a condition that sum of the covariance sequence divided by n square. That quantity goes down to 0 as n tends to infinity. That is, we considered weak law of large number. So, for that, what is the condition we established? That exercise are sequence with finite mean and variance, and if in addition to that covariance of xi, xj, if double summation I j not equal to I, if I consider the double summation divided by n square, if that goes down to 0, then xi will obey the weak law of large number. Then we consider the special cases. If xi's are i.i.d, if xi's are independent, if xi's are uncorrelated, then weak law of large numbers are satisfied. For strong law of large numbers, we saw that we need this special condition, that is independent and identically distributed sequence of random variable. A sequence of independent and identically distributed random variables was considered in the case of strong law of large number, SL and Ln, strong law of large number. So, xi's are i.i.d, they are i.i.d, and we proved it, that is with finite mean and variance, but we imposed another condition, that finite fourth order central moments. What does it means? That is E of xi minus mu to the power 4, that is finite. In that case, what we proved, that this Sn by n, that is the sample mean, will converge almost sure to the true mean. So, this is the strong law of large number. So, that way we establish two of the very important results in probability, that is strong law of large number and weak law of large numbers. We discussed weak law of large numbers in more details, but strong law of large numbers, a special case of that we covered. So, next we will cover another important result, that is the central limit theorem. Thank you.